Okay, good morning. Welcome to
SuperMath174.
SuperMath174. So we were looking at, and we went back to a section we had skipped in our geometry book today and looked at regular polyhedra. Although we didn't mention it during the conversation we had today, do you know there's another name for some of these special regular polyhedra that we looked at?
It's the platonic solids.
Platonic solids. And in the book they mentioned an interesting thing to look at, vertices minus edges plus faces, and fortunately we have some of these regular polyhedra 3D print things. So first, can you show how to fold these up?
Well, this is an octahedron, and it folds up. It's made entirely out of triangles. Folds up like that.
Cool.
It's probably not going to stay folded up once I set it down.
I hope it does. Good.
Mostly. And here's the cube.
And what special property does this particular cube have?
It glows in the dark.
It glows in the dark. Do all cubes have that property?
Nope. Just this one.
Just that one. Okay, so let's count. Let's do it. Vertices minus edges plus faces for a cube.
So the vertices, there's 8 vertices. Minus, it's a little hard to write sideways. Edges, there's 12. Plus faces, 6. Which is 2.
Alright. And how about for an octahedron here?
Octahedron vertices, 6. Minus edges, 12. Plus faces, 8. Is 2 again.
Cool. So what do you notice happening here?
Well, to go from the cube to the octahedron, you just flip the 6 and the 8.
I wonder if that means something geometrically.
Well, I know that a cube and an octahedron, they're duals of each other.
Alright, what does that mean?
Well, that means you can, like, if you draw an octahedron inside a cube with each vertex at the midpoint, at the middle of each face, then you can create a regular octahedron that way.
Well, that's amazing. So we see from this formula that there might be a relationship between a cube and an octahedron. And just for fun, let's do the dodecahedron and icosahedron too.
Alright.
Okay, so can you bring those over?
Dodecahedron.
Here's our dodecahedron. This is just a big 20-sided die, and this one actually we have.
And folds.
We printed it out and it folds up. Okay, so what about? Can we do that one first?
Icosahedron.
Vertices of an icosahedron, vertices minus edges and faces.
So the vertices of an icosahedron, well, there's 2 at the top and bottom, and there's 5 across here, 5 across this way, and then that's it. There's 10.
How'd you get 10?
So, oh wait, 12. 12.
So how do you count them again?
So the way I counted them is I'm looking at it like this.
Okay.
You've got 2 on the top and bottom,
Alright.
5 across the top, and 5 across the bottom.
Okay. So that's 12 vertices.
Minus edges. If you look at it like this again.
You need to get it a little bit more towards the middle and get your hand out of the way.
So, just sort of prop it up like this. So, you've got 5 edges going down.
Alright.
5 going across the top.
Okay.
And you have the same thing on the bottom. So it's 20. But you still have more. You have the stuff in the middle. So if I start at this, if I start here and count, 10. There's 10 vertices, edges in the middle. And then plus faces. I already know that there's 20 faces on an icosahedron.
Okay.
So 12 minus 30 plus 20 equals 2.
Equals 2. Okay, cool. Now, knowing what you know from that, how can you count the vertices, edges, and faces of a dodecahedron quickly?
Well, flip these.
Okay, why?
Well, because there's 2 pairs of duals in the platonic solids. There's the cube and the octahedron, and the icosahedron and the dodecahedron.
All right, so how can you see that if you connect up the middles of the faces of the icosahedron that you get a dodecahedron?
Well, because they're grouped in pairs of 5.
Uh-huh.
So if you connect up the middles, you get pentagons.
Look at that. How cool. So we don't actually really have to do that much more work to do vertices minus edges plus faces for a dodecahedron. It's 2. Pretty neat. Here's an unfolded dodecahedron.
Yep.
It's pretty cool, I'd say. All right. Where have you seen this formula before?
I think we did that graph theory project. It was there.
Yeah. So it seems to be holding true a little bit in 3 dimensions as well. All right. Good job.